Hello everyone! Welcome to Lesson 2.8, the derivative as a function. In this lesson, we'll be finding a specific function in order to be able to solve for the derivative of f of x at any given point. First, let's do a little review. We already know how to find algebra slope of 2 points of a function. This is given by y2 minus y1 over x2 minus x1, where x1, y1, and x2, y2 are your points. Previously, we went over how to get the slope of the tangent line to any given point on a function, given by the limit as h goes to 0 of f of a plus h minus f of a over h when you're trying to solve for the tangent slope at x equals a. This, however, only gives us a numerical value that is specific to a certain point. It doesn't really help us out with the rest of the function. What if we could come up with a function that would give us the slope of the tangent line at any given point? Good news is, we can. Instead of using a numerical value, let's use x. Instead of h, let's use delta x in order to represent the change in x values. What we're doing here is taking the slope of 2 points on a function and making the 2 points come infinitely close together, or taking the limit as delta x goes to 0. In the end, we can find the derivative function by taking the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. With any function f of x, all we have to do is take the limit using this definition and plug and chug. Sometimes, however, the derivative function isn't continuous. There are 3 special cases that we have to keep in mind. Number 1, absolute value functions, or sharp turns. Number 2, piecewise functions, or where the original function has a hole or a jump. And number 3, finally, functions that have vertical tangent lines. Let's go over examples of each one of these and explain why the derivative function isn't continuous or the function isn't differentiable in these cases. Example 1, absolute value equations. Y equals the absolute value of x. In order to solve this function and understand it, we have to split it up into a piecewise function. In order to keep the absolute value for all x values less than 0, the function must be multiplied by -1 in order to keep its value positive. All x values greater than or equal to 0 may remain the same. When we solve for the derivative function, we have to do something similar, splitting it up into a piecewise function. This way, we get the limit as delta x goes to 0 for all values less than 0 equals -1. We find that the limit as delta x goes to 0 for all values greater than or equal to 0 equals 1. The left-hand and right-hand limits don't equal each other, and that's a problem. Let's graph both the derivative and the absolute value functions to investigate. Here, we see that the derivative function isn't continuous. There's a jump in the graph. Therefore, the function is not differentiable. Example number 2, piecewise functions. Y equals x squared for all x values greater than or equal to 0, and y equals 1 plus x for all x values less than 0. In order to take the derivative of this function, we must take the derivative of the 2 parts of the piecewise function separately. Doing so, we get that the limit as delta x goes to 0 for all x values greater than or equal to 0 equals 2x. So now we have a function into which we can plug in x values to find tangent line slope. We find that the limit as delta x goes to 0 for all x values less than 0 equals 1. So tangent slope and the derivative function for those x values is constant. Uh-oh. The 2 functions don't equal each other again. Let's graph all of the functions together so that we can compare them. As we can see from the graph, the derivative function isn't continuous. There's another jump in the graph. The left-hand and right-hand limits do not equal each other. Therefore, the original function is not differentiable. Example number 3, functions with vertical tangent lines. F of x equals the fifth root of 2 minus x. This function is pretty complicated, so for this one, let's go straight to graphing it to observe the vertical tangent line. We can see on the graph that at x equals 2, the function makes an extremely steep decline. Making a tangent line at x equals 2, we can see that the tangent line is vertical, making its slope undefined. Since the derivative is equal to the slope of the tangent line at any given point, we know that at x equals 2, the slope of the tangent line, or the derivative, is undefined, making the derivative undefined for this function. The function is not differentiable. Now, let's go over some important notation. In calculus, we like to find the derivative of a function with respect to a variable. Most of the time, we find the derivative of a function with respect to x. As you can see here, the derivative function is denoted in what looks like an algebraic ratio. The derivative is denoted by dy over dx, which means the derivative of the function y with respect to x. You can also write this as y prime or y with a tick mark next to it. What's cool about derivatives is that we can take them infinitely many times. We can take the second derivative, or d squared y over dx squared, by taking the limit as delta x goes to 0 of f prime of x plus delta x minus f prime of x over delta x. This can also be called y double prime, or y with two tick marks next to it. We can do a similar process for finding higher order derivatives, such as the third derivative, or d cubed y over dx cubed. We simply take the limit as delta x goes to 0 of f double prime of x plus delta x minus f double prime of x over delta x. The same rule and school of thought applies for the nth derivative. Some common mistakes include substituting 0 in for delta x prematurely. This leads us to get, as you can see here, an answer of infinity, negative infinity, or no solution, which is not generally the right answer. Another common mistake is misinterpreting the graph of the derivative and the original function. If the derivative is spitting out negative y values, that means that the derivative at that x value is negative. Even though the slope of the derivative on the graph may appear to be positive, if it's spitting out negative y values, that means that it is negative. On a calculator, this lesson tends to be pretty simple. You mostly just want to simplify the derivative function as much as possible before plugging it into your calculator, and you need to make sure that you're using appropriate parentheses when needed in your calculator so that the calculator doesn't get confused. For the most part, it's pretty simple, and you just need to plug and check. That concludes our lesson. Thank you so much for watching. For extra practice, see the worksheet provided in the link. Happy calculating!